Han Liang, who is a graduate student, has this, I'm generator of bad ideas, and he's a filter, and when he does something, it's correct. When I do something, it's wrong. So almost everything in this talk will be correct, because Han has had fundamental ideas in it. 3 theorists walk into a bar. Now, this happens in 1984. They order 1 lattice scalar, 5, 4 each. It comes in up flavor and down flavor. So what is this plus minus here? So this is explained in the fundamental paper, and of course, Gamanu said, no, thanks, I'm not drinking tonight. So he just David it. So when they go low, we go high. So David chooses minus. A very wise choice. There is a whole life that follows, and this is taken from a really nice paper by David and collaborators like Sergey. And it's all oscillatory, kinky. There is some heavy breathing that comes in. There are beautiful things like intrinsic localized modes, etc. And Predrag takes the high road. So I take plus. And I notice that, there is a lattice constant when you are in discrete time and space. So if I take the high road, this is really like taking imaginary mass or imaginary coupling for the oscillator, or you're inverting the potential, that's what's going on. And what happens there is everything is hyperbolic, nothing is really true, it's all hyperbolas. It's unstable, it's turbulent, it's utter chaos, and no sensible person would go there. The material boy takes the low road. Eventually, this goes all the way to FPUT. It's a materials world, it has amazing impact. The cat, dark black cat, takes the upper road. It's pretty, but it's not obvious that's nearly as important. It only purports to solve the problem of turbulence, which is one of the few small problems we have left over from 19th century. The main thing is to realize that when you have this 1 over mu square, you can change the lattice constant for time. And if you do it, it's a very nice Laplacian equation, and it has a name. It's a Klein-Gordon theory, so for scalar bosons. Who would have guessed that that's Klein-Gordon theory? But that's what it is, just a little change of sign. Some people here are over 37, you might want to space out. So the only thing you need to remember from this whole talk is that, when you have stability, you're computing eigenvalue as a real matrix, it's like 50-50. You can get complex eigenvalues, or you can get real eigenvalues. If you get a complex ones, then you have oscillatory eigenmodes, you have crystals, you have solid-state physics, you have all kinds of stuff that they teach you in the school now. Since 70s or 80s, certainly since 70s, in physics, we've been also teaching the other 50% of the coin. It could be hyperbolic, unstable, it could be chaos, it could be turbulence. The weird thing, please correct me, it seems to me nobody has taken the high road before. There is this amazing book and this introduction by David, all about 5-4 theory. And to the best of my ability, I cannot find the minus sign case anyplace in that review. It just isn't there. I might be wrong. And there are other reputable books. So, for example, Leo Kadanoff, in his statistical physics book, explains very well oscillatory physics. He uses Gaussian field theory to explain it. And there's some critical value of delta x in that case, or some other parameter he calls capital K. And when that border is crossed, he says, I'm not going there because dragons live there. So now I have to report, we have breached into this domain hitherto reputed unreachable. I apologize, I'm not doing this in original French. And we report back that only kittens live there. This theory has always been there in plain sight, and somehow I missed the turn when we were getting to it. So it's in Abramovich and Stegun. So someplace you learn that if you know anything about sines and cosines, you just have to take imaginary argument, and then they become hyperbolic sines and cosines. And what it means in present context, very often when you solve a problem in oscillatory regime, for example, you compute a Green's function or something, oscillatory regime, you just take sines and cosines to hyperbolic sines and cosines, and voila, you've solved what I will call turbulence or chaotic problem. And one way you can think about it, and I'll come back to it a few times, when we make a transition from few degrees of freedom in mechanics or in quantum mechanics to many or infinite many degrees of freedom, then in quantum field theory, we tend to think of ground state as lots of oscillators. There are lots of oscillators, and then stick little glue into this thing that's called nonlinear coupling, quantum chromodynamics, quantum, some perturbative little thing, and they start interacting. But basically, the basic idea of this kind of theory is there are basic modes of oscillations, and we might call them particles, boson, electrons, etc. And then there are interactions, and you put in there. Sergio Brie comes in here and says, well, what about situation where I'm balancing kinetic terms, which is coupling to my neighbors, versus potential terms? And in most of this perturbative theory says, a really important thing is there is an electron, there is photon, and sometimes they couple. It's some weak thing, and then we develop, perturbation theory. What about if what's really important, and there is a very heavy meson, very heavy somebody, and sometimes they look to their neighbors, so this is the other end that's called the anti-integrable limit. And I disagree with Sergei. It is anti-integrable limit. It's not, just because you can solve it, as you'll see in my talk, doesn't mean that it's stable, in that sense, integrable. It's not a circle, it's hyperbola, what happens out. And now you don't think about oscillatory modes anymore. One thing that you could take home with you, if you are, childless and like cats, the world of turbulence is filled with cats. So, I'll make it very literal because I'll discretize space-time, and on every point in space-time there'll be a cat. And now, they're different cats. They're tabbies, they're black, they're orange, etc. So they have different kind of states. And now you go and you push a cat, give it a little nudge, and unlike the harmonic oscillator, it has an anti-hook law. You push it, it runs away. So every place these guys are running away, and that's why Kadanoff didn't want to go there. He feared this idea that everybody runs away. What do we do with everybody running away? Oscillations, I understand. They come back, so I can, it's controllable. It's part of the state space. They can't run very long. That's why we have nonlinear field theories. They put boundaries that say, I cannot have cat that exceeds speed of light and stuff like that. There's a bounds to what cats can do. They have to come back, and that's called ergodicity, recurrences, etc. So you have to figure out now, it's a very different topology of the space. It's not little concentric circles, KM, etc. You have to connect it, but we are very happy to have had, Boltzmann, Maxwell, etc. before us. So, that's domain or ergodic theory. They come back and we have to figure out how to do it. Why would you want to take a high road when the low road is so profitable? And it's an intellectual thing. I look at the clouds, and our friend Mitchell Feigenbaum, by saying, you look at these things, do you believe that there is a Cray computer in the sky solving Navier-Stokes equations? No way. I mean, that's obviously a stupid idea. So these guys solve the equations effortlessly, and we labor here forever, in a stupid way. So how does that work? We call it turbulence for shorthand for many nonlinear phenomena. It doesn't have to be fluids or anything. So that's one reason why I want to figure out how it works. So you can think of this way. It's not correct, but it's a starting picture. In the old days, when people had to sit in prison to wait for execution, like Landau or other gentlemen had nothing but thinking. they had some kind of ideas how turbulence might work. Those ideas didn't work out because the only things they could think about the oscillations heading and up and lots of Fourier things. That wasn't a good idea. But, they gave us some laws, like, there is some scaling that engineers shouldn't care about, but we care about, stuff like that. But, that's all very crude because today, 100 years later or so, you can actually see turbulence, you can simulate it, you can measure it, and this is a numerical plot of turbulence in pipe. But it could be experimental data. It's comparable accuracy you can attain today in measuring turbulent phenomena. And the first thing you realize about turbulence, it's not about that its spectrum is 7/13 or something k to the minus of. You can see the shapes, and those shapes recur, and you can identify. If you're a graduate student, you can look at the turbulent flow, and you can say, oh, Reynolds number was 2,400. Because you can see in the flow all the shapes. So our task to understand turbulence is to understand the shapes of turbulence, in my opinion. The naive idea is you can do this very well today in this millennium for small computational domains. We do this for infinite pipe approximated by a pipe which is shaped like a beer can. We can do that computation. We cannot do the whole pipe. Well, this talk is about how to do it at infinity. And the idea would be, I would take these shapes. Can I put from them the vocabulary which says turbulence can be A7 to 24, something, like weather patterns that we collect. And can we from them glue what turbulence really is? It's here, I'll describe it, but it's actually not like that. I mean, it's more sophisticated than this picture, but that, can motivate you. Now, you might be an H-bar person and you couldn't care about stuff that's not physics. Why would you care about stuff like that? But many-body chaos, it's many-body physics, and in this room we think that's important. So in that case, what you can take home, the traditional field theory that tries to describe many-body chaos or quantum chaos in quantum field theory, it's like you start with Helmholtz. You have a spring mattress, you jump on it, and you study its properties. Now, chaotic field theory is different. It's called damped Poisson in applied math literature. It's called Yukawa in quantum field literature. And it's chaotic, meaning nothing oscillates. Everybody runs away, so everything is unstable. So this is kind of two extremes. And on the left-hand side, there are few situations where you have exactly integrable models. On the right-hand side, it's also very hard to find exactly chaotic models. But, there are very few. The real life is someplace in between, but to understand it, I'll focus only on the extremely chaotic models. One way that most of us have been taught how to think about it is semi-classical field theory. Through this talk, I'll use lattice field theory because, for me at least, it's easier to understand what's going on when I look at discretized modes rather than starting continuum. Essentially, same theory should work for continuum theories instead of many coupled ODEs for PDEs, partial differential equations. But I'm not sure that there won't be some minds in there that we haven't run into yet. But discretized field theory is very nice. So, discretized field theories, you have a parquet floor, and you put the answers on it, various places. And, you make sure they're comparable height so it doesn't look too ugly. So you get some distribution, and you replace a continuum field, in this case, a scalar field is only one value per lattice side, but it could be a multiple of values. It could be things with spins and God knows what. And you replace it by a discrete set, and that makes it easier to think and compute things. Now, the question that we would like to answer if we have really theory of turbulence or terror, we would like to be able to predict how likely are we to see certain weather patterns, certain shapes, certain phenomena which are consistent with the laws that govern them. You want to understand long-time behavior and large space behavior problems, not short-time. That's a different technology. We would like to find a probability that, the dancer is 5.6 inches tall or something like that. So we want to do probabilities. There is a very standard thing which is a path integral, so Dirac-Feynman way of thinking about quantum mechanics. So the idea there is that there is Hilbert space, only there are some amplitudes. They have interpretation of being probability amplitudes. So they're not probabilities, but amplitudes. But other than that, things are very similar. And any particular configuration, which is here capital Phi, has some probability correctly normalized, so they add up to 1. And to correctly normalize, you have to form partition sum. You have to look at all probabilities together. That's called a path integral. So one way to try to understand it is to look at, a very honorable 1920s way of understanding quantum mechanics, which is Wenzel-Kramer's brilliant semi-classical approximation. And it's classical because it'll turn out that you will connect quantum mechanics and then quantum field theory to something people tend to understand, which are classical solutions of classical equations. And it's semi because the way it turned out to be complex way they come from quantum mechanics. The way the nonlinear complex fields work, like they have a landscape. There's lots of hilltops, saddles, valleys, etc. The stationary phase is a method of saying, what's really important about this integral comes from Laplace is stationary phases, because there the main contributions lie, and they could be hilltops, bottoms, saddles, etc. If you twiddle this thing, that's called variational calculus, the extremal points do satisfy classical mechanics. A century later, that turned out to be the main thing. The result of this is that amplitude is given by the determinant of the Hessian, and this thing at the bottom. And the theory is called Gutzwiller trace formula for quantum mechanics. And what you take home is you have a landscape, and its backbone are classical solutions. And there are lots of, why are there lots of them? Because that's called chaos. So the theory that only keeps the saddles, I'll call it deterministic field theory, is built on periodic states. Periodic states is something that has some period in time, some period in space, and for every continuous symmetry, it has a period in that direction. Locally, it satisfies what I'll call Euler-Lagrange equation. Globally, it satisfies boundary conditions. Now, if you go back where we started in that bar, on the left-hand side is a theory that is called 5-4 theory. But that's an example of Lagrange equation. Where this thing is 0, that's what we are looking for. And other examples are what I call spatiotemporal cat and phi cube, 5-4 theory. And basically what you say, I try all possible field values, and I use variational method to make at every lattice side make the thing go to 0. That is a space-time solution. So you think globally and you impose equations of motion as local constraint. And you get periodicities. So here are a few pictures of what periodicity could look like. You can think of it as bricks. You can think of it as primitive cells. You can think of it, and that's again Serge-Aubry, you can assign symbolic dynamics by using anti-integrable limit of these models. And the last thing in this picture is the same as these two, lower right corner. Good luck if you can see it. And if you do this in continuum, you can do this, for example, Kuramoto-Shivashinsky. You can tile the space with spatial-temporal repeats. So we can compute them. We have GitHub where you can go and download and compute them. Another question is, okay, so I have lots of solutions. How important is any solutions? I don't want to know infinity of them. That's organized by what's called stability exponent. It's nothing mysterious. In determinism, you demand that the law is exactly obeyed. That says it's Dirac delta function. There is only one point in high-dimensional state space that obeys the law. You screw it up a little bit, it's not allowed. You know how to integrate the Dirac delta functions. When you do this, you get the same orbit Jacobian I computed for quantum mechanics without square root this time. Most important thing is to understand perturbation. Here I learned something from Arkady Pekovsky. When people do chaos, they do perturbation which has same periodicity as periodic orbit, but that's wrong. Everything we did was wrong. You should actually perturb it in a full state space, which means not just periodic space. So you should compute functional determinant on infinite space, and that's called function, so that's scary. It turns out you can do it because solid state people know how to do it. And that gives you an exact deterministic weight, which is conveniently stated as the exponent, stability exponent, which is to spatiotemporal chaos, etc., what Lyapunov exponent is to temporal evolution. Now, this is exact. There are no approximation because this is all deterministic. Everything we taught, Ruel, Gutzwell, myself, in time evolution is wrong because our perturbation space was too small. Now, in this audience, you know what I'm doing. You actually have to compute bands in stability space. What we used to compute are just points on these bands. We actually have to do those things. We have to integrate over them. And now we can do this in 1-2 dimensions. And now I'll pause for a second because somebody might tell me this obviously has an analytic answer, this integral stability in 2 dimensions. It's some modular function. It's some elliptic function, K, or some Dedekind function or something. Please tell me what it is because we compute it numerically being just plumbers. We don't know how to do it. Here we are. We know how to determine importance of a single state in this deterministic space of all solutions. Now, deterministic field theory says put them all together. As we put them all together, we get a sum directly. And this sum is amazing. So this is deterministic partition sum. I simply take all of my solutions. Each one of them has a weight, which is stability. There is something that has to do with entropy right there. And then there is something that has to do with observable I want to compute. So just a number that's associated with any solution. And it's raised to the volume of the primitive cell, meaning the number of lattice states in one of these periodic domains. That's this exponent. And that's just a number. It's incredible. This is really partition sum, and it just adds up everything, and that's the answer. And it's the exact answer. In semi-classical theory, it's approximate. So now, what's chaos for field theories? Somebody who lives in space-time is not stuck to just marching forward in time. It has Hill determinants which are exponentially expanding, and it has exponential number of periodic states. And that is chaos in space-time. And notice there is no time in this definition. It so happens Hill and Poincaré have proven that the 2 conditions are consistent. They're the same, but this is how you think of it now. Well, that's interesting what Cvitanović says. But it's not physics, is it? Stuff that we consider turbulence chaos, it's beautiful stuff. Like the simplest example, I take a known map and I get this amazing fractal attractor. That's beautiful, right? This is some stupid formula. This is not physics. So, secret, you rewrite a known as a recurrence equation. You rescale it a little bit. You introduce new coordinate, which you call Klein-Gordon mass. And what do you know? This is phi cube theory. It's the same theory. One is written stepping forward in time in Hamiltonian formulation. The other is in Lagrangian formulation, it's, in space-time, but the other one generalizes to higher dimensions. So, 3 theories walk into a bar. One says, that's me. And I tell this my graduate students, if you have a symmetry, you must use it. The 2 other guys, get up, say, here we are is a crackpot. They leave the bar, and I'm left alone. And, so now I'll do my dance, which has been alone for like 20 to 30 years. You don't use partition sums. That's stupid. You should use zeta functions. Why? Because Euler says so. We know this forever. Because whenever you have a symmetry, you should count orbits. You shouldn't count states. Because every state in an orbit is related to each other by symmetry. So there's only one object that's called orbit. So your theory should be in orbit space. If you see something, you should make sure that you include a prime thing, first time it happens, and all of it repeats. So that's illustrated on this slide. So Selberg trace formula, or what we call partition sum, is some of the old states, but they're related in subsets which are, just one object. So you write it in terms of orbit. That's called deterministic. I'll call it Royal zeta function in this case, but it has long history in math. And it was actually discovered by Euler in 1882, this particular one in 2 dimensions. And, it was hard to evaluate, so for about half century, people developed theory of elliptic functions. So it turns out this orbit, for each prime orbit, this zeta function has a name. It's called Dedekind zeta function. And it's a modular function. It's beautiful stuff. And we are sweating over what's the best way of computing it, because the theory is infinite product. For each prime cycle, you have one of these zeta, Dedekind zeta, and you have to understand how to average over infinite product of all prime orbits of the classical deterministic theory. Now, why does this work? It's infinite. There's something called shadowing in hyperbolic systems. I'll just show a picture. These are 2 states, large states on space-time. And you can't tell it, but within black square, they have the same Aubry symbolic dynamics that comes from anti-harmonic limit. Outside, they differ. And when you compare their distance, see how distant they're from each other. These are fields, a bunch of dancers over the whole room. You discover they're exponentially close at the center, exponentially decay. What's all this good for? We can make predictions. Any observable you give me, like where is neural waves are dissipating energy, I should be able to compute it. There's a formula if I have all my wave solutions, and I should be able to compute it. Bye-bye, that's it. Old stuff is oscillatory, new stuff, 3rd millennium. Remember, time is stepping forward, even though I'm in space-time. If it's too difficult, your problem might be oscillatory, might be hyperbolic. They're both good, don't be afraid. And there we are.
Thank you very much for that. Thank you for a very interesting talk. I wish we had more time.
Well, the deal was that somebody would drag me off the stage. I was going to do Feigenbaum, and just keep going on and on and on. But you're not forceful enough.
No, I'm not.